들어갈게요. All right, so we see 1.3, we did 1.3, right? This is 1.4. Euler method. All right. So what's the idea in an Euler method? Okay. Let's say this is the graph of integral chord right here. Okay. Then this is t-axis and the y-axis. Then let's consider the differential equation dy dt is f of t comma y, and then with the initial condition. So this is the initial variable problems. Okay. So what are you gonna do? Um, we're gonna chop the time intervals. Okay. So here, starting from the initial time, t's sub 0. And then let's say T1 is T0 plus H. H is just, the difference between T0 and T1. Okay. And the T2, T3 is kind of discretize the time interval into many sub-intervals. Okay. So this is the first sub-interval. This is second sub-intervals. Okay. This is third sub-intervals. So maybe here is T3, maybe. Okay. T3. Right? Okay, so we do not know exact solution. Okay, we just assume that we do not know exact solution, so that we do not know integral chord, because we don't know, this is obvious, right? We do not know exact solution. How can you figure out the integral chord? No. Okay, impossible. But just let's say this is integral chord. I know it sounds weird, but let's just assume that this integral chord right here. Now what are you gonna do? We're gonna find out the tangent line. Okay, we're gonna find tangent line at the initial point, initial condition. Okay, so we know how to find out the equation line, which is tangent of that integral chord, right? How can you do that? Because we know point slope form of the line, right? Y minus y0, y sub 0. This is the initial condition, right? Is equal to m times t minus t0. This is, normal, regular, the equation of the line, right? Especially point slope form of the line. But how can you find out m? Because the t0 and the y0, this is given in the initial condition, right? That's the initial condition. Okay. But how can you find m? M is what? The slope, right? Because this is a tangent line, what? Of the graph of a function of this graph, right? But this is the graph of exact solution y of t, isn't it? Okay. Yeah, we do not know y of t, but we know y prime. Where is y prime? Right there. This is y prime, right? Y prime is equal to f. F is given in the problems. Okay, this is a source function, which is given in problems. We know this. So the meaning of this one is dy dt, which is slope of the tangent line of y of t, exact solution y of t. So m is y prime is dy dt. This is equal to f of t comma y. Okay, so this is given, so we plug in this one into m. Yeah, so y is equal to y0 plus, f of t0 y0 t y0. So, okay, so we got the equation of the tangent line at t0 y0. So we're gonna use this line to approximate approximate y at t1. Listen carefully. We're gonna use this equation, which is the equation line, tangent line at t0 y0 to approximate y at t1, t sub 1. So y of t sub 1, this is the exact value of y at t equals t sub 1. Okay, right here. But this is unknown. This is unknown. But since we figured out that tangent line, so we can figure out y sub 1 by plugging t sub 1 and then t sub 1 into here, right there. You see, right here. We plug in t sub 1 into right there. Then we can find out the y coordinate of this point, which is, let's say, y sub 1. Okay, we can use this one as approximation of y of t1. Because I don't think, I mean, yeah, you see the gap between 2 points. I don't think this is a good approximation. Yeah, you are right. I'm with you. I don't think this is a really good approximation of y of t1 because there is a big gap. We can see that. But when h approaches 0, h's get really small, maybe 0.001, something like that. Then so the t0 and the t1 is really close, then the 2 points will be really close too. So y sub 1 will be a really good approximation of ty of t sub 1. Okay, so let's say y of t1 is this is approximated by, this is approximate, okay? So this one is approximated by y sub 1. Y sub 1 is just evaluation of that tangent line, equation of tangent line at t equals t1, so right here. And then we see that t sub 1 minus t0, this is actually h, okay? H is what? The difference between t0 and t1, right? Okay, and then what about T2 and difference between T2 and T1? Assuming that we discretize the timing number uniformly, evenly, I mean, then H is actually what? T sub I minus T sub I minus 1. Here, I equals 1 through D, maybe N, okay, right? If we, chop the timing number to N sub-numbers. So right here, let's see, is t sub 0, t sub 1, t sub maybe k, okay? T sub k, oh, let me say I. T sub I, the t sub I plus 1, there's a t sub n, okay? And then h gonna be ti minus, okay? So here's a question, okay. I mean, this is kind of side story. That integral chord, yeah, it's kind of, yeah, just, it looks normal and then it's regular. But what if it's just the solution, behavior solution looks like this? Hmm, okay. Then you see that the solution sharply increase at a specific time interval. Yeah, then I don't think it just that Euler method is gonna work when with evenly, discretizing. So from here to here, it's okay, just discretize evenly, okay? But we need to have something to, capture that kind of sharply increasing behavior of the solution. We may need to discretize locally more, okay? So that is called the adaptive scheme, adaptive technique. So when you go to the MATLAB, I think ODE 15 in MATLAB, that command will be optimized for finding good approximation of solution having that kind of behavior. The ODE, you normally use, I think you guys use ODE 45, that command in the MATLAB, but there are ODE 15, ODE, I think 35, ODE 45, there are all different type of the Runzikutta-based numerical method code in the MATLAB, but for each one has a specific benefit. Okay, So this is called the adaptive or refinement or local refinement. Okay. And then that kind of behavior is called the boundary layer. Okay. This is an out of the this subject, but yeah, maybe it's good to know about this one and know that yeah, the terminology is boundary layer effect. Okay. At the boundary, it sharply increase or decrease the solutions. Normally, regular, numerical method cannot capture that kind of behavior. We have to do something. Okay, so that's the not main part right here. All right, so let me repeat this. Okay, so at T1 right here, also to find out approximation at T sub 2, what are you going to do? We're going to use Y sub 1. Okay, we just going to construct the tangent line at T1 and Y1. I'm not saying Y of T1 because this is the exact value of Y at T equals T sub 1, which is we don't know. Because we do not know the exact solution. This is unknown. Okay. So instead of that, we're gonna use the T sub 1 and Y sub 1 to find out the equation of the tangent line. Okay. So then Y sub 2 is equal to Y sub 1 plus, there is M, right? Here is M at T sub 1 and Y sub 1. Because we know that M is slope is f of T comma Y, right? M is equal to dy dt. That is equal to f of T comma Y. So we use the function f, source function, which is on the right-hand side of the differential equation, and then evaluate this at T sub 1 and Y sub 1. Okay. And then times T2, T minus T1, okay? And then we plug in T2 into T, that's gonna be approximation of Y of T sub 2, okay? So, yeah, so right here, then we're gonna get, Y sub 1, Y is equal to, Y is equal to Y sub 1 plus and the F of T sub 1, and then Y sub 1, and then T minus T1. That's going to be equation of tangent line at T sub 1 comma Y sub 1, which is this. And then we use this one to find out approximation of Y at T sub 2 right here. So now you can see that we got more, we got, the that approximation, the gap between, Y sub 2 and the Y of T sub 2 is, bigger than this one, right? So now we can expect that as time is marching, the quality of approximation just getting poor and poor. That's the actually problem in a Euler method. As time is marching, then the gap between, this is error, right? The error between the approximation and the exact solution is getting larger and larger. That's a big problem. Okay. Then how about Taylor method? How about the Runge method? So the Taylor method is a general method, the numerical method to by generalize the Euler method. Okay. And then all Taylor method has same problems. Okay. But Runge method is a little bit different. Yeah, just different than from the Euler and Taylor method. Anyway, so repeating this process, so finally we got Euler's formula for T sub n plus 1. This is exact solution at T sub n plus 1 is can be approximated by Y sub n plus 1, which is Y sub n plus F, and this. But this is H, right? And this is equal to H. This is equal to H. Okay. Okay. Now, this is Euler formula. Okay. Let's see example. Mm, right here. Okay. Example. So y prime is equal to minus so half 1/2 y minus t plus 3/2. So this is f of t comma y. Okay. Just for example, I mean, so how can you find the f? Do I say just, uh, okay, right hand side always f? No. Okay, you need to isolate y prime and the left hand side first. Okay. Then the right hand side gonna be must be f. Keep in mind that. Don't make mistake. So read the initial condition right here, and then find out y sub 2. I mean approximation of t sub 2 when h is 0.2. This is a timing the step size. It's called the step size. Okay. So t see right here, and the t sub 0 is right there, which is 0. The t sub 1 gonna be what? T sub 0 plus h, right? But h is t sub 0 is 0, and then h is 0.2. So this is equal to 0.2, right? Then right here, t sub 2 is going to be 0.4, isn't it? Okay. So question is to find out approximation at t sub 2, which is y of 0.4. And so we need to find out approximation of this guy, which they say y sub 2. Okay. Using the Euler's method. What are you going to do? We got to find out y sub 1 first, right? Y sub 1 is what? By that, Euler formula is going to be y0 sub 0 plus f of t0 y0 times h. Just do this. Okay. Then you can get 1.2. And then, plug in 1.2 into what? Here. The t sub 2 is what? 0.4. T sub 1 is, I mean, actually, this is h, right? That's h. Okay. This is, what is f? Right there. It's given. Negative 1/2 times y minus t plus 1.5. Okay, 3/2. Then y2 gonna be 1.34. Okay, so now what are you gonna do? Well, sometimes you want to see how much this number is close to the exact solution. You may want to figure out the accuracy, right? If we know the exact solution, there are two ways to find out error between the exact solution and the approximation. The first one is just compute absolute error. Sorry, let me zoom in. The absolute error. Oop. Okay, absolute error is just do this. Find the absolute value of the difference between exact solution and the approximation. Okay. Why is okay? Okay. That's the exact solution. This is approximation. But this one they take a maximum. Take a maximum. Okay, n. So when n is 1, 2, 3, 4, 5, and so just for all n value of n, we compute the absolute value of this difference and then take a maximum value. That's going to be absolute error. Absolute maximum error. Absolute maximum. The second one is relative error. You find out maximum of y of t sub n minus y sub n over and then absolute value of y of t sub n. Okay. Oh, no. It should be maximum of absolute value of y sub t sub n, like this. Okay. But sometimes, and depending on textbook, sometimes they don't compute the maximum, just this. I think that should be enough. Okay, it's n. Okay. So why we need to why just we divide the value of exact solution? Why? Because think about this. Yeah, exactly. So let's say, y sub t sub n is equal to, for example, 0.001. Okay. And then y sub n is equal to 0.002. Then absolute error gonna be what? Absolute error is gonna be what? It's gonna be 0.001, right? Oh, that's good. 0.001, 10 to the negative 3, not bad. But when you compute the derivative error, 0.001 divided by what? 0.001, which is 1. Well, we divide the difference between absolute error by the you know the magnitude of the exact solution. Why we got the 0.001 as an absolute error? Because y of t sub 1 is small already. That's why the absolute error is we're gonna get this number. So when you just relative error give us more kind of accurate error in the sense of in the common sense. Okay, so normally we use relative error instead of the absolute error because absolute error may be kind of biased. All right, so that's the Euler method. And then what about this? That means this is actually Taylor's series, isn't it? So when you take a look at this, y sub n plus 1 is y sub n plus f times this one. It's kind of the Taylor series, right? Isn't it? Of y, right? The value of the Taylor series of y centered at t sub n and evaluating that Taylor series at t sub n plus 1 and then cutting into at second term, right? If you just, this is a Taylor series of y centered at t sub n, and they cut the, let's say this is 0th term, okay? And then this first term. Okay, let's say this first, okay, the second. Just cut into second term, and evaluating this one at t equals t sub n plus 1, we're gonna get exactly the same as this. So actually this is what? Yeah, this is Taylor series. Taylor, or you can say Taylor polynomial. That's why I told you Taylor series is general, uh, the Taylor method is the general method for in terms of the Euler method. And the Euler method is based on the Taylor polynomial or Taylor series. Okay. So here's a pseudocode. Starting point, which is initial conditions, and the Euler formula right there. Okay, and then we increase t sub n. Okay, this is the increment of the t time. Okay, so we plug in approximate solution, which is this one using we're gonna find out the value the y sub n using the Euler formula at t equals t sub n. Okay, and then let's say that is y sub n. Right, and then repeat this process. That's just the pseudocode of the Euler formula, Euler method.